Hello, everybody. Good morning, good afternoon, good evening, whatever time zone you are in. My name is David Trilling. I'm talking to you today from Northern Arizona University in Flagstaff, Arizona, United States. And I'm going to talk to you today about asteroids in the solar system as seen by NASA's Spitzer Space Telescope and James Webb Space Telescope. I want to do a little orientation before I get too deep into that topic. This is a map of the world, of course, and the red symbol is showing you the European Southern Observatory in Garching, Germany, which is hosting a conference this week on infrared astronomy. And this talk that I'm giving is part of that conference, and there are hundreds of people from all across the world who are attending that conference virtually. And the blue dot, as you see on the left of the globe, is Flagstaff, Arizona, where I currently am sitting. In case you haven't been to Flagstaff, let me show you how beautiful it is. We live here at 2,300 meters. The picture on the left is typical fall day in Flagstaff. The top of our mountain is 4,000 meters. And on the lower right, beautiful snow-capped mountain that we'll have soon in the winter here. Many of you may have been to Flagstaff. If you've been on the way to the Grand Canyon, it's about an hour from my house. Flagstaff is a lovely place. The Grand Canyon is amazing. One thing you might not know about Flagstaff is that we are the world's first international dark sky city. In addition to my university, we also have here the Lowell Observatory shown in the top left. That's a historic, more than 100 years old observatory where Pluto was discovered. And we also have the United States Naval Observatory here in town. So please come and visit us when it is safe to do so, not before then, but when the world is safe to travel again. I look forward to having you here in Flagstaff. Here's another part of our orientation. This is the solar system. You live here. This is a plan view of the solar system. So we're looking down onto the solar system from way up above. And this is not just a cartoon, but an actual map of the solar system. And each symbol, dot, colored symbol here on this figure shows the location of a specific object in the solar system at the time that we made this map, which was a few years ago. So this is really a freeze frame, a shot of what does the solar system look like at this particular moment in time. So let's look at that. The sun is this yellow star right in the middle of the solar system. Earth's orbit is this blue circle that I've just added. So the orbits of the major planets are the thin blue circles, and Earth is the thick one that I've just added, just so you can see where it is. Main belt asteroids are the green symbols, and there are 700,000 or so of them that are shown on this diagram. And these orbit between Mars and Jupiter in our solar system. And then the near-Earth asteroids are these red symbols. And we're going to talk a lot about near-Earth asteroids today, so I wanted to highlight them on this map. Near-Earth asteroids, the main thing I want you to know is that near-Earth asteroids are asteroids whose orbits bring them close to the Earth's orbit, and that the Earth orbits in this swarm of near-Earth asteroids. Everywhere the Earth goes, we're surrounded by near-Earth asteroids. Okay, take the labels off. Now we zoom out. It's the same figure as before. And this is now the outer solar system, so showing Jupiter, Saturn, Uranus, Neptune, those orbits. And again, bodies in the outer solar system. This is a map of where those distant objects were at the time that we made this map. And I marked Pluto here just so you can see where that is as well. So the point of all of this orientation is to show you that the solar system is full of little tiny bodies. Most of them are asteroids. And also to give you a sense of the scale of the solar system and how do all the parts fit together. Okay, a couple more definitions, then we get into some science. So this is an asteroid. It is a rock in space. This is a meteor, which is when that rock has entered the atmosphere of the Earth, and you see a flash going across the night sky. And you might call it a shooting star. There's other names for it. And this is a meteorite, which is a rock that made it all the way to the ground. So an asteroid is in space, a meteor is in the atmosphere, and a meteorite is on the ground. Okay, so back to this map. I've given you some orientation here. I want to focus now on near-Earth asteroids, and that's going to be most of the rest of this talk. So a reminder, it is these red symbols here that are all around the Earth as the Earth orbits the sun. Okay, why do we care about near-Earth asteroids? One reason is that near-Earth asteroids come from elsewhere in the solar system. They didn't originate near the Earth, they came from other places and have ended up near the Earth's orbit, which means that by studying near-Earth asteroids, we actually are studying other places and other pieces of the solar system that are not very close to the Earth. So instead of us going to visit all those distant locations, material from those locations has come to the Earth or near the Earth where we can study it carefully. Another reason is that near-Earth asteroids are our nearest neighbors in space, the closest thing to the Earth. In fact, many of them are even closer than the moon as they fly by the Earth. So if you want to go explore space, either scientifically or as an astronaut in exploration, the first thing you do is you go to the nearest neighbors. So those are near-Earth asteroids. Near-Earth asteroids can be explored with spacecraft, and we are presently doing that. Several countries around the world have done it in the past, are presently doing it, and will be doing it in the future as well. And finally, near-Earth asteroids sometimes hit the Earth. So here's an example of that. This is obviously a cartoon, not a photograph, from 65 million years ago, when an asteroid or maybe a comet that was about 10 kilometers across hit the Earth. It killed off the dinosaurs. It changed the climate of the Earth for a very long time. It gave rise to the origin or the dominance of the mammals on Earth and eventually humans. One thing I really like about this picture is that the T-Rex just looks like it's laughing at its fate in the universe as this asteroid comes to hit the Earth. Asteroids don't only hit the Earth in the ancient past. Here's an example of something that happened about 50,000 years ago in Meteor Crater, Arizona. That's about 40 kilometers in this direction from me. It's about east of here, about a half-hour drive. And this is a case where a 50-meter sized asteroid hit the Earth, created this crater, which is about 1.2 kilometers across. It killed a lot of animals in this area, but it didn't cause global destruction. But a lot of regional destruction was caused by this impact just down the street. And some of you may remember that in 2013, in February, there was this thing happened over the city of Chelyabinsk in Russia. Let me show you this little movie here. It's just 1 minute long. This is a meteor and then meteorites. So the videos you're going to see here are from dashboard cameras from different people's cars. And you can see that streak across the sky. This was evening time, so it's commute time. These are videos from security cameras, and you can see, again, the flash in the night sky, or the evening sky, I should say, as people were commuting home. Here's another dashboard camera video. You can see this meteor in the atmosphere. And the explosion in the atmosphere shattered windows all over the city and collapsed the roof of this factory. And that's my last part. Okay. So as I mentioned, impacts are not just something that happened millions of years ago or even tens of thousands of years ago, but this one was about 6.5 years ago. This is a person who found a meteorite on the side of the road. He's holding it in his hand. I actually bought a piece of the meteorite on eBay. I'm sure everything that's sold on eBay is exactly as it's described. This is a lake outside the city, and there's this amazing hole that was in the ice that covered the lake, where a piece of the asteroid that became a meteor, then became a meteorite, landed in this lake and made this hole, this little tiny crater, basically, and you can see people there, this hole in the ice on the lake. And in fact, some divers went into the lake and recovered this piece of the asteroid, which is just amazing. I don't speak Russian, but I can tell that this wrapper says meteorite on it in Cyrillic, which I think is super interesting. Okay, so asteroids hit the Earth, and they do it all the time. Okay, let me go back to our map here, and I've given you all these introductions, and now we're going to start to talk about some of the science that we've been doing with these telescopes to study near-Earth asteroids. So as a reminder, the science goal here is to understand the origin and properties of bodies in near-Earth space. Those are all the red things on this plot. And as a reminder, these are our nearest neighbors. We can carry out robotic exploration. Sooner rather than later, we will be carrying out human exploration as well. And we want to understand potential impactors, hopefully before they hit the Earth, so that we understand what is coming our way. Okay, so as promised in the title of my talk, I said I was going to talk about the Spitzer Space Telescope, which was launched by NASA in 2003. On the right here, I'm showing you an artist's rendition of what the telescope looked like in space. So let me give you some details. The primary mirror was 84 centimeters, so you could hold it comfortably in your hands. The telescope was in an Earth trailing orbit, which means not orbiting the Earth, but actually drifting away from the Earth as time went on. From 2003 to 2008, the telescope executed a cryogenic mission. So it was launched basically with a refrigerator on board with a certain amount of cryogen to keep the telescope cold. After 2008, the cryogen ran out, and we operated the telescope for the next 12 years in what we called the warm mission mode. It was still pretty cold, but not quite as cold as the cryogenic mission. And as I mentioned, in this Earth trailing orbit, it was drifting away from the Earth, which is why we don't have a picture of this telescope in space. So this image here is just our guess of what it would have looked like in space. And the important thing about the Spitzer Space Telescope was that it was an infrared telescope. So we observed at infrared wavelengths, or infrared light, which is not what you can see with your eyes. It's a different wavelength of light, and it allowed us to measure the heat coming from asteroids. And that's the key part to all the other things we're going to tell you, is that we measured this heat coming from the asteroids, which allowed us to do a number of interesting science investigations by measuring that heat. Okay, so that's the Spitzer Space Telescope. It was used for many different science investigations over 17 years, 16 and a half years. We focused in particular on studying near-Earth asteroids. So our team observed 2,132 unique near-Earth asteroids. That's about 10% of all of the near-Earth asteroids that are known. So remember that image or the diagram that had the red band of asteroids near the Earth's orbit? We observed about 10% of those with this telescope. So it's a quite substantial fraction of the population for us to learn new things about asteroids and what's near the Earth. For each asteroid, we measured the diameter and what we call the albedo, which is simply the reflectivity. So think about you might have a white wall or a white shirt or something which is highly reflective. That would be a high albedo. Or if you had a black pavement outside or a black shirt that you were wearing, that would be a low albedo or low reflectivity. So those are the two things we measure for each of these asteroids: the diameter, which is just simply the size, and then also the albedo or reflectivity. So for diameter, my third bullet here, infrared measurements like the ones that we've done is more or less the only way to measure diameter for thousands of asteroids. If you want to do one or two, there's other ways you can do it, but if you want to do a whole lot, the only real way to do it is using this infrared technique. And when we measure the albedo, or the reflectivity, that corresponds to a composition for an asteroid. So for every asteroid, we're measuring its size, and we're also measuring something about its composition. And we do this for 10% of all of the asteroids that we know that are near the Earth. Okay, so I'm going to show you in this talk not a lot of figures and plots, but some to show you some of the data that we've acquired. So on this figure, I'm showing you on the bottom is diameter in kilometers. So you can see on the right side is 10 kilometers, then there's 1 kilometer, and then 0.1 is 100 meters. So that's the size of a soccer field, football field, is 100 meters. So we're measuring asteroids as small as that, and in fact, some are actually quite a bit smaller, would fit easily inside of a soccer or a football field. And then on this vertical axis on the left side, I'm showing you albedo, which again is just reflectivity. So from those two things, and this is our 2,132 asteroids, I'm showing you that at the top, we can measure the size distribution. So we measure the number of asteroids that there are at whatever size. And that tells all of us, how did these asteroids form? How did they evolve? How did this population evolve? And it also tells you something about what is the likely size of the asteroids that are going to hit the Earth. There's some number of small ones that hit the Earth every day, very small ones, and they just are meteors and they don't make any catastrophic impact. And then the very big ones, of course, would be a huge disaster for Earth. And so we want to know how many impactors there are of each size. On the right side, I'm showing you that we also measure a range of albedos from the very dark to the pretty bright. And that is telling us about a distribution of compositions in the near-Earth asteroid population. So from this plot, this is the sort of summary of 12 years worth of work of 2,000 asteroids that we measured. We measure the number of asteroids as a given, how many there are of a given size, and then we also measure their compositions for each one of those asteroids. Okay, we also measure, in addition to size and composition, we're also measuring light curves. So what is a light curve? Here's my example asteroid again in the upper left here. And this asteroid looks like a potato. All asteroids look like potatoes, more or less. Imagine that you have a potato, and you pick it up and you start to rotate it in your hands. Sometimes you'll be looking at the narrow end of the potato, and that's the circle I've got in the lower left. And sometimes you're looking at sort of the elongated, the fat side or the wide side of the potato, and that's this sort of elongated ellipse that I have in the second cartoon. Circle to ellipse, circle to ellipse. What you see when you look at the asteroid is that it appears to get brighter and fainter and brighter, look at my hands right, and fainter and brighter and fainter as it rotates. In other words, by observing these asteroids, we measure their shapes, their elongations. So here's 4 asteroids on the right side. These are some data from our survey. On the bottom is time in minutes. On the left axis is just brightness. And you can see that they get brighter and fainter and brighter and fainter. In other cases, we observe just part of a rotation where the asteroid gets brighter. And we don't see the whole thing, but we see some part of it. When we combine all of that together, we can make a plot that looks like this. So on the bottom, I've got diameter in kilometers. Again, now I'm showing you 10 to the 1 is 10 kilometers, 10 to the 0 is 1 kilometer, and 100 meters, sorry, is off to the left a little bit. And this vertical thing is elongation. So at the top is more spherical, at the bottom is more elongated. And okay, there's big error bars here, but you can kind of draw a line through it that says the big ones are spherical and the small ones are elongated. Okay, so that's telling us about the shapes of the asteroids. And the fact that the small ones are elongated is telling us about the internal strength of these asteroids, because these small ones are created when 2 big ones collide. By producing elongated ones, we can measure the amount of strength needed inside that asteroid to keep that shape. Okay, I have a few individual objects I want to talk to you about. This is, like my family tree. I'm not going to tell you about all 2,132 of my cousins, but I'll tell you a few of them. Here's one. This is a detection of activity from an asteroid called Don Quixote. So this is an image from our data in the top right. The little bullseye pattern in the middle shows where the asteroid is. And it's a little bit hard to see on the screen, but moving upward from that bullseye is kind of a gray fan shape. And that's a cometary tail. So what we discovered is this thing that we thought was an asteroid, is actually a comet. Here's another one, 2 actually, that we talked about, that we measured with the telescope. These are 2 asteroids called 2009 BD and 2011 MD. I apologize for the names. They are 2 near-Earth asteroids, And in fact, both of them, we measured the sizes to be about 5 to 6 meters. Okay, so that would actually, you can't see my office. Here I'm in my office. You could fit one of those asteroids inside my office. Not both of them, but one of them you could. In the lower left, again, I'm showing you an image from the telescope. And this inset box in this image is showing you our detection of the asteroid. And you can see it's just a few pixels, right, where we detected the brightness. But we have a very sophisticated technique of analyzing the data and turning those pixels into real science results. So let me show you on the right side, these two rainbow colored plots. I'm going to start with the one that's all the way on the far right, which says mass on the bottom. This is in tons, actually. And then the vertical part is the geometric albedo, which again is just reflectivity. From low to high tells us about the composition. And I just want to show, I'm not going to go through the details, but show that we can estimate the mass of this asteroid as well as its composition based on this result. This panel in the middle I do want to talk about a little bit more, the one that says bulk density on the bottom, and again, geometric albedo on the left side. So bulk density is, you know, how dense your thing is. Is it metal? Is it rock? Is it whatever it is? And on this scale, the density of water is 1. And you can see from our color diagram here that the reddest color is the best solution. And so the best solution is right around a density of 1. And then again, we have this albedo solution. So density of 1 means this asteroid has about the density of water, more or less. And some of our solutions you can see are less than 1, which means this asteroid would be less dense than water. What does that look like? Well, on the top here, we have an artist's conception. Nobody knows what this asteroid really looks like, but we suggested that it might be a pile of rocks moving through space together. Each of the rocks is the density of rock, more or less, but together there's so much empty space that if you could put this thing in a bag, it would float in water if you could find a swimming pool big enough. And in this picture at the bottom, there's a swimming pool big enough. So all you need now is a big bag, and then you can do the experiment. Okay, finally, I want to talk about this, our last of our individual objects, an interstellar object called Oumuamua. So an interstellar object is something that originated in another solar system, passed through our solar system, flew out the other side, going somewhere else. You all are now experts in looking at images from the Spitzer Space Telescope. You can see in the top right, there are no pixels there that look like we detected it. In fact, this is a non-detection of this object. But it's still very interesting. With the non-detection, we can place a limit on the amount of gas and dust coming off of this body. We can place a limit on the albedo, or the reflectivity. It was higher than it was expected. And altogether, these results add to the mysteries of this body, Oumuamua. Where did it come from, and where is it going? Or what is it made out of? Okay, I mentioned that Spitzer, I talked about my cousins before. That was a joke about asteroids, but I really do feel like Spitzer is a family affair. I just wanted to tell you this story as well. We worked together for a very long time on this project, for much more than a decade. We had a small, very tight-knit group that spent a lot of time together and really enjoyed always working with each other. Part of the process of the Spitzer project was we had to write proposal deadline. We had to write proposals to meet various deadlines. So there was a deadline in February 2005. That was 2 days before my daughter Madeline was born. Here she is. She's now 15 and a half. There was another deadline that was in November 2007. That was about a week before my son Gabriel was born. Here he is. He's almost 13 now. There was another deadline in February 2017. And the day of the proposal deadline, my close colleague Michael's son Tim was born. He's now, how old is he? 3.5. And then the end of the Spitzer mission was January 2020, and 1 week after the end of mission, Michael's son Paul was born. And this is a picture from, Paul was a few days old. Now he's 10 months old. So I just want to share that, for me, this is a very personal, not just scientific, but a personal endeavor. And our kids are growing up and have grown up alongside the Spitzer mission. And so I really feel attached to the mission in a very personal way. Okay, so that was the end of the Spitzer mission in January 2020. Now what? Now we talk about the James Webb Space Telescope. So this is NASA's next space telescope. It will launch in October of 2021. The plan is to have a 5-year mission, and the telescope will be far outside of the Earth's orbit. So this middle figure in the bottom that looks like it's in space, this is a cartoon. And this the gold pattern here is the mirror of the telescope, which is 6.5 meters across, so quite large mirror. And underneath that mirror in this cartoon picture are these gray layers, and those are thermal insulation to keep the telescope cold and make it extremely sensitive. In the very bottom right corner of that picture, you can see Earth in the distant background. So this is just to show you that this telescope is far away from Earth. In the upper right, I've shown you, this is an actual photograph of some engineers working on the telescope at one of the NASA centers. And again, you can see the gold panels. Those are the mirror, together make up the mirror of the telescope. And if you look carefully, you can see 2 humans in this picture. They're wearing these white bunny suits. One is in the upper middle and one is in the upper left, standing on an orange platform. So that shows you the scale of how big this telescope is. It's really enormous, and it's going to be a tremendous telescope in space. So what will JWST be good at? That's the James Webb Space Telescope. We'll be very good at observing very faint and distant things. What will James Webb not be good at? It will not be good at observing near-Earth asteroids, it turns out. So there's a couple reasons for that, but one is, remember that picture I showed you before, this telescope is enormous, and it doesn't move very fast on the sky. So asteroids flying by the Earth go quite fast. The telescope cannot move fast enough to catch up, to keep up with those asteroids. And so James Webb will not be very good at observing near-Earth asteroids. It's going to be a great telescope for a lot of other things, but not for observing asteroids. So how do you observe a near-Earth asteroid now that the Spitzer mission is over and James Webb is not really going to do what we need? The answer is that we can use ground-based infrared telescopes. So as I mentioned at the beginning, this public talk is associated with a conference that's being run at ESO called Ground-Based Thermal Infrared Astronomy, Past, Present, and Future. We are talking about ground-based infrared astronomy, and that is the place that we're going to go to continue to study near-Earth asteroids. So here's one of the facilities that we can use. This is called NASA's Infrared Telescope Facility on the mountain of Mauna Kea in Hawaii, the big island of Hawaii. Some of you maybe have been there as well. Beautiful picture. And inside this telescope, we are building or rebuilding really this instrument called MERCI, which is the Mid-Infrared Spectrometer and Imager. This picture on the right is a little bit hard to see, but the orange thing at the top of the picture is actually the top of the telescope, and we're standing underneath the telescope looking up at the telescope. And in the red box is this instrument MERCI. So we are just starting a new program. We're going to use MERCI to observe hundreds of near-Earth asteroids every year to measure their diameter and albedo. So all of the science things I told you before that we've done with Spitzer, we're going to be able to do, to some degree, some of those on the ground with this new instrument on this telescope in Hawaii. Okay, so here's my summary. We're right at just about at 30 minutes. It's perfect. So I have a few summary points for you. One is asteroids are interesting. I think they're interesting. I hope you think they're interesting now too. And I would say that near-Earth asteroids are especially interesting for the reasons I talked about, that they sample other regions of our solar system, that they are the nearest neighbors to the Earth, and of course that they sometimes hit the Earth. Infrared observations give us unique information about near-Earth asteroids. It's pretty much the only way you can measure this kind of information for a large number of asteroids. You want to know their diameters, you want to know their compositions, their shapes, their strengths. This is the right way to do it. I hope I've convinced you that Spitzer was an absolutely terrific facility. It was a pleasure to use Spitzer for so many years. That the James Webb Telescope will also be great, but I also have to mention that it will not be perfect. It will not be the best asset to study near-Earth asteroids. And therefore, we're looking forward to using our new ground-based capability that will be available soon. So thank you for your attention. I see that there's some questions appearing. I'm going to stop. I'm going to go over and read the questions out loud, questions, comments, whatever you've got, and I'll try to answer them as best as I can. Thank you. Okay, so I'm reading now questions that I think are showing up in the YouTube chat, if I understand how this works correctly. So the first question from Martin, thank you for your question, Martin. How was the diameter measured and distinguished from albedo? So I'm not sure which slide exactly you were referring to, but let me see if I can answer this question generically, and hopefully it will make sense. When we observe the heat coming from the asteroid, which is what we do with our infrared telescope, what that tells us, as long as we know where the asteroid is, which is how far away it is from our telescope, the amount of heat corresponds directly to how big of the asteroid it is. Okay, a small asteroid, you see less heat coming off of it. A big asteroid, you see a lot of heat coming off of it. I guess the analogy would be if I have, it's a hard one, maybe a small light bulb and a big light bulb. It's not quite exactly right. Okay, so let me just not take the analogy because it's a little bit confusing what I just said. We measure the diameter by measuring how much heat. Then by knowing what the diameter is, and we also, I didn't talk about this, but we measure our asteroids in the optical as well, like with your eyeball. If you know how bright it appears to your eyeball and you know what the diameter is, then you can measure the albedo, which is the reflectivity. So there's a few steps in the logical chain. And we actually have calibrated this technique very well using a small number of asteroids where we make a bunch of different kinds of measurements and ensure that our model is appropriate and accurate. So thanks for that question. Jacqueline asks, are the asteroids colliding between them? The answer is yes. We don't think we've seen that actually happen. So there's a lot of asteroids out there. I showed you this map with all the different symbols. Asteroids are certainly colliding. They're certainly colliding, but there's a lot of empty space. So it doesn't happen very often. In our programs, we have not seen this, but other people who are doing different kinds of measurements with different telescopes have seen that occasionally an asteroid will suddenly grow a tail and then the tail will go away. And then maybe another asteroid will do that a few years later. And there are several interpretations, but one of the interpretations is that there was a collision, one asteroid hit another, it spit up a cloud of dust, and we were able to see that from the ground. Okay, let me move. Questions are coming in. This is great. Thank you. So Martin asked another question. If there's still time left, can you elaborate how the mass was calculated? Okay, that was a fun one as well. So this is an asteroid. It was 2011 MD was the one that had those rainbow plots where we calculated the mass. That one passed very close to the Earth, and we were able to measure the orbit of the asteroid extremely well, much better than we mostly are able to do. And what we're able to measure is that the orbit of the asteroid deflected slightly from the sort of Kepler's laws or the usual expectation of where the orbit would go. And it deflected slightly because, believe it or not, the photons from the sun, the sunlight from the sun was actually pushing on the asteroid and changing its orbit just a little bit. Okay, so we could measure how much the orbit was changing using this, not our measurements, but some other measurements. But what you don't know is, you know how the orbit is changing, but you don't know how big the asteroid is, and therefore what the mass and the density are. So if you put all those things into the right equations, which I actually cannot write to you right now, but maybe some other time I could write them down and see if I could remember them correctly. The amount of deflection of the asteroid depends on the mass of the asteroid. And so a smaller mass asteroid would be deflected more easily, and a more massive asteroid would be deflected less easily. So we measure the deflection, and then that tells us the mass. Our team measured the diameter. If we have the mass and the diameter, then we measure the density. And that's how we determined that the density was more or less the density of water, plus or minus, which is why I showed that picture of the big swimming pool. Okay, let's move on. Nora Lee says, albedo usually refers to reflectivity of solar radiation. So how is this related to infrared radiation? It's a really good question. Let me see if I can explain this in a good way. So it's a hot day, you go outside, you're wearing a white shirt, or let's make it easier. You're wearing a shirt that is white on one side and it's black on the other side. And what you feel on your body is the black side is hotter than the white side, because the white side is reflecting the sunlight back into the sky, and the black side is absorbing the sunlight and making you hotter on that side. So that's the albedo and the reflectivity, as you said, the solar radiation. But if I looked at you wearing your black shirt and your half black, half white shirt with a thermal camera, what I would see is that one half of you is hotter than the other half. So by measuring the heat coming off of you, I can infer or deduce or calculate what was the albedo or the reflectivity of your shirt in the optical. So how it's reflecting the solar light. Okay, here's another question from Maggie. For detection of asteroids composition, carbon, metals, hydrocarbons, etc., is there also classic spectroscopy used? Yes, it's a very good question. Thank you, Maggie. So spectroscopy is a much better way to measure the composition. So spectroscopy allows you to measure the molecular composition of something, a rock or dirt or a plant or whatever you're trying to do. And it's a technique where you observe at many, many, many different wavelengths, and you can use that signature to understand what are the materials in the thing that you're looking at. We were not able to do some spectroscopy of these asteroids that we talked about, and so we have this sort of proxy where we think that we know the albedo corresponds to the spectroscopic composition. It's pretty coarse, so I don't have a really good ability to say it's definitely this thing and not this other slightly different thing. With spectroscopy, you could make that differentiation, but with our albedo measurements, we just say it's either this kind or it's this kind. So we have a very coarse way that we distinguish between bodies. It's the best we could do. Spectroscopy would be better. And in fact, for some of these asteroids, we did a totally separate project where we used a ground-based telescope. We obtained spectroscopy of a small number of our asteroids to do this correspondence or calculation. How do we relate the spectroscopy to the Spitzer measurements to show that our relationship was a good relationship? There was a good fidelity in that correspondence. So it did work out, but there's some extra steps involved. It's a really good question. Okay, Victor says, are you able to measure the Yarkovsky effect with infrared telescopes from Earth? Are they sensitive enough? Victor, this is a very sophisticated question. So the Yarkovsky effect is what I mentioned before about an asteroid whose orbit is deflected due to the solar pressure. You could, in principle, measure that with infrared telescopes from the Earth. The fact is that the infrared telescopes are not as sensitive as the optical telescopes. And if you only want to measure the deflection of the orbit, you're better doing it in the optical because you can make more precise measurements. But what you can do in the infrared is you can measure the detailed properties of the surface that might help you constrain the Yarkovsky effect, which is this thing that pushes the orbits. So you could, for example, measure, I didn't talk about this, but you could measure the thermal properties of the surface material. How well does it absorb sunlight? How well does it re-radiate the sunlight? And that would also allow you to understand this Yarkovsky effect. Excellent question. Thank you. Okay, Olga says, good day. Good day, Olga. Are you going to observe NEAs in BVR optical bands in the same time as in the IR? You guys are asking, these are good questions. Okay, so with Spitzer, I'll start there. We observed only in the infrared. There were no optical channels or visible light channels on the telescope. We did do a small campaign where we used a ground-based telescope in the optical at the same time as the Spitzer telescope in space, again, to sort of make a correspondence between our data sets. Olga says, oh yes, because you need the V data or the optical data to derive the diameters and albedos. So let me now advertise, at the very end, I talked about this instrument Mercy, which is going on the telescope in Hawaii. So our team has rebuilt this thermal camera, the Mercy camera that observes in the thermal infrared. And the telescope team in Hawaii has attached to it an optical camera, which is called MOC, which is the Mercy optical camera. And it simultaneously points at the same piece of sky as the infrared camera. And so with a beam splitter, we can send the optical light to the optical camera and the thermal light into the thermal camera. And so we will simultaneously observe in the optical channel and in the infrared. And then we'll do exactly what you said. We'll get simultaneous optical and V data, and then we'll derive the diameters and albedos to very good precision. because that simultaneous observation allows us to do that. So thanks for that question. Okay, so we're approaching the time, and thank you all for your excellent questions, and for everybody who attended this talk or will attend this talk in the future if you're going to watch some streamed version of it. Thank you again to the questioners and allowing me to try to explain those things to you all. And now I will sign off. So thank you very much, and have a good rest of your day or night or wherever you are.